we're going to get to chemistry. Now, this is a common pitfall. Somebody a few years back, they thought that, okay, we are going to cover basic chemistry because, again, high school chemistry is a prerequisite. And actually, at most four-year in universities, chemistry is a prerequisite for this class. But because some majors require this in the first year, college chemistry is not a requirement. So there was one student who took like advanced chemistry and biology, and they thought exam one was all review. No, and they bombed hard when we got to the tissues and integument because they skipped out on class. So for those of you who had AP chemistry or already took Chem 161, you might find this all being a review, but you should at least come back for tissues. But again, this is going to be very basic level. I'm not going to cover everything in basic chemistry, and again, that's why there's a whole year course for that. Okay, so this is an atom. So you might, when you think of the word atom and you haven't had much chemistry, you might think of this. And this is like what you might see a lot in like old art or in stylistic. It's very attractive in terms of a logo, but atoms aren't quite like this. Or the thing is that they're not like planets orbiting the sun. In fact, your book says it's more like an electron cloud. But even then, you might think like, okay, does that mean this entire thing is an electron? And this is the nucleus? Not really. So electron cloud just shows the possible places where an electron might be found. So I know this is really hard to see in the static image and make you think like, is the electron just a bubble? But I think this is a little better representation of an electron. So as you can see here, all these little dots appearing in the swarm. So things that electrons are actually always buzzing around this cloud. So there's a certain amount of electrons depending on the atom. But the thing is that electron cloud is just all the possible places. But notice that, look at that GIF right here. So notice that the electrons are not all orbiting like planets. They're kind of buzzing around. So this I think is a better representation of what electron cloud is. All right, so let's talk about subatomic particles. Now, there's only three I expect you to know. If you're studying things like string theory or quarks, you're studying way beyond the scope of this class. So protons, so this is one of the ones you need to know. Neutrons and electrons. So these are the three subatomic particles that I expect everybody to know in this class. All right, so protons, so these have a positive charge. So it's a very easy mnemonic. Protons are positive, they both start with P. And they have so this is a relative unit, but they have one mass unit. And this is found in the nucleus. So the location of the proton is important. And neutrons. So neutrons sound like neutral, right? And therefore they have no charge. So there's no electrical charge. And they have an equal mass. So they have a one mass unit as well. And they're also found in the nucleus. So the nucleus, that center part, and actually this is the thing about nucleus in this class. You're going to find, I think there's at least 4 different definitions of nucleus in your textbook. So here we're talking about atomic nucleus. So whenever you see that term nuclear, it usually refers to the center of something. But again, you be very careful. There are multiple definitions throughout this course. And electrons, unfortunately, they're not called electronegative charge. They just have a negative charge. It's not an electron. It's electrons. These have the negative charge. So common mistake, people think neutrons have a negative charge. No, neutrons don't have a negative charge. Electrons do. So these have a relatively tiny mass. So compared to the one mass unit found in the neutrons and protons, they have a very, very small mass compared to those two. In fact, a proton has just over 1,800 times the mass of an electron. So the majority of a mass of an atom is from protons and neutrons. Electrons do contribute, but they're a very small drop in the bucket compared to protons and neutrons. So these surround the nucleus, as we saw in the previous animation. These buzz around and swarm around the nucleus. They do not orbit like planets. And why do they buzz around? That's more for quantum physics. I think that's like a 200 level physics class. And again, if you're going to the health sciences, unless you're going to maybe radiology, you don't need to worry too much about that. All right, so subatomic particles. So here's a chart summarizing all of the subatomic particles. So again, main thing is that I want you to definitely know the charges of each of these particles and their relative size. Do I want you to memorize the mass units of electron? Not really. The main point I'm getting at there is that electrons are really tiny, even though I'm showing them like relatively smaller. I mean, if I showed them to scale, you wouldn't be able to see them on this image right here. So let's talk about how these subatomic particles are arranged in an atom. So here we have the protons, and again, protons have a positive charge. And then we have the neutrons, and the protons and neutrons. So again, neutrons, neutral, they do not have a charge. So this makes up the nucleus. And again, nucleus is some sort of center structure. That's one thing that is in common between all the definitions of nucleus you'll find within this class. So again, these are your nucleus of an atom is made out of both protons and neutrons. Well, except for a special case we'll get to really soon. And remember, those electrons, they're swarming and buzzing around the nucleus. So again, they're not orbits in terms of like, they're called orbitals, but they don't orbit like planets. I know it's kind of confusing at first, but take my word for it. So again, electrons, these have negative charge, and they're surrounding in electron shells or electron clouds that are surrounding and buzzing around a central nucleus. All right, so then this is the thing. So let's talk about what is an atomic number. An atomic number defines what elements are. So the number of protons, so the number of neutrons and electrons does not determine what an element is. It's the number of protons. The count of the protons determines an atomic number. So here we have, so when you see the periodic table, you notice that it's a grid and it has all these like numbers. It has all these like abbreviations and the full name. Well, not all periodic tables have it, but this is like a typical thing you would see in the cell of the periodic table. All right, so again, this is the full name we see right here, and this is the atomic symbol we see. So it's typically abbreviation. Now, this is and another caveat. Sometimes, like especially in English, it's not necessarily abbreviation of the full name, like things like sodium. Sodium's atomic symbol is not SO. It's actually Na. And up here, this is what we call the atomic number. So so the atomic number is 2 for helium. How many protons are there in helium? Count them. 1, 2. So atomic number is always the number of protons. So again, atomic number, number of protons, that determines what element atom is. Right, atomic number. So what if you could change the number of protons in an atom? So I mean, it take sophisticated scientific and expensive scientific equipment to actually do that. But say something weird quantum mechanics things happen, and all of a sudden an atom gains a proton. So here we have carbon, and so how many protons are in carbon? Hint, it's somewhere in here. Yeah, so remember, atomic number is the number of protons. So there are 6 protons in a carbon atom. So carbon, notice that the carbon, this is both carbon. Here we have a diamond, we have a coal or graphite here. So yeah, one of those things. But notice that depending on how it's arranged, it's the same thing. So again, they all have, all the atoms in here, they all have 6 protons each. So this is carbon, and again, look at it, it's solid. It's hard, or sometimes in terms of graphite, it's pretty soft. But what happens if some random reason carbon gains a proton? Is it still carbon? Well, no. Notice that the atomic number went up because now it has 7 protons. In fact, if you look at a periodic table, what's number 7 on the periodic table? It's not carbon, but it's nitrogen. Is nitrogen the same thing as carbon? Definitely not. So you might be familiar with liquid nitrogen, but actually you're looking at nitrogen right now. In fact, the thing is about the nitrogen you're looking at, it's invisible. 78% of the air we breathe is nitrogen. So it's like a common misconception. The air we breathe is 100% pure oxygen. It's not. Most of it by volume is nitrogen. So again, if you actually this used to be back like in better economic times when Ala Moana first opened that new wing. They had this place called Nitrogeny, And the thing is that they used to make ice cream using liquid nitrogen. But one thing you may have noticed is that they had these big ventilator ducts, these big silver ducts that were pumping air out of nitrogeny. It wasn't necessary to pump out the good smells inside, but the thing is that when you have liquid nitrogen and then you're starting to cause it to evaporate, that releases nitrogen gas in the air. So the thing is that with air can only fit in certain amount of molecules and atoms inside a certain volume. So if you have all this nitrogen being released, that's going to take up the space where oxygen is. So it's actually going to make the oxygen concentrations less. So if you don't get rid of the excess nitrogen, all the workers and all the staff inside nitrogeny would end up suffocating. So again, this is why you want good ventilation if you're working with liquid nitrogen. Okay, so then nitrogen is not the same as carbon. So say we add another proton, something else happens. Is it still nitrogen? Well, look one cell to the right on the periodic table and you have oxygen. So is oxygen is it the same as nitrogen? Again, just one difference of one proton and you have something radically different. This is the one we need for aerobic respiration. This is the one we need to live, right? So this is what we're breathing in and trying to get enough to supply our cells. So again, just the difference of one proton makes it very, very different between each atom. So this is why it's important to know that atomic number. So protons determine elements. So it can have variations in the neutrons and electrons, but protons, that's what determines the chemical symbol. That's what determines the elements. So this is another way to think of it. Protons determine properties. Protons are positive. Protons determine properties. Or you might also think of it. So again, carbon, different from nitrogen, different from oxygen. And between carbon and nitrogen, you only have a difference of one proton versus nitrogen and oxygen. You only have the difference of one proton. So reading the periodic table, so let's talk about chemical names. So these are the essential elements you need for physiology 141 and 142. So the thing is that you don't need to memorize the entire periodic table, but I expect you to know the full names of all of these elements right here. And I have arranged it in a certain way where the elements here on the left, these are ones you'll see more often. And these elements here on the right, you probably won't see them. Actually, you probably won't even see them in PHYL 141. You might see more of them in PHYL 142, but they're kind of rarely referred to. But all of these in the first column, second column, and sodium chloride, you definitely need to know for PHYL 141. So you need to know the full names of all of these. And be careful. Remember that Fe does not stand for I and Fe. I is not iron, it's iodine. Fe is actually iron, but it comes from the Latin ferrous. So this is why we have, like, sometimes you have a little curveball thrown at you in chemistry. Okay, so what if you could change the number of neutrons in an atom? Okay, so this is what we call isotopes. So isotopes, here we have carbon, we have 6 protons. Everything looks great, right? Everything looks normal. Say it somehow gains a neutron. Is it still carbon? And yes, it is still carbon because why? It still has 6 protons. So a neutron does have 1 atomic mass unit and it is equal in weight to a proton. So what happens is that this carbon atom, it did gain a neutron, it's still carbon, but now it's 1 mass unit heavier. So this is what we call carbon 13. But if we add another neutron to it, you might have heard of this if you've like things like history and archaeology or radiology. So what we have here, is it still carbon? Again, the number of protons did not change. It's still carbon, but now it has 14 atomic mass units. So again, you have 6 protons plus 8 neutrons in carbon 14. So this is where, if you see this little number in the upper left corner of an atomic symbol, that means it's the amount of, that's what we call. So again, in carbon 11, 12, 13, 14, it's carbon. It's going to have the same amount of protons. Yep, it got heavier. So again, 5, 6, 7, 8. So you can change the number of neutrons, but you're not changing the element itself. You're just changing the overall weight of that atom. So all of these are still carbon, but they're what we call different isotopes. They're not the same thing as each other because they have a different number of neutrons. So this is what we call our mass number. So the number of protons plus the number of neutrons is what you call the mass number of an atom. So a carbon-14 atom is heavier by 2 neutrons than a carbon-12 atom. So this is one way, and there's more. If you're more interested in about this radio labeling, maybe you want to go into radiology or take more advanced chemistry questions. So yes, you can have lighter and heavier isotopes. So this is what we call our mass number, and they're roughly corresponding to, okay, remember, electrons, it can change, but protons and neutrons, way more massive, like almost just under 2,000 times the mass of an electron. So this is why protons and neutrons together contribute to the overall mass of an atom. So again, different isotopes have different mass numbers. And if you haven't covered that in chemistry, I'm pretty sure that was like part of Chem 161, although that was like over a decade ago. But you will cover this at some point. All right, so last, the subatomic particle. So again, change the number of protons, you change the element. Change the number of neutrons, you have different isotopes. What if you could change the number of electrons in an atom? And this happens in cells all the time. So here we have fluorine. So fluorine, now what it has is, okay, how many protons does it have? Hint, right there, right? So say we have 9 protons. Now what do we have surrounding here? Are those neutrons? Yeah, they're electrons, right? So they're electrons, but thing is that fluorine, so we're not, okay, in this class, I think your book does mention it, going to be concerned with valence and how many X amount, like in terms of like which orbital has how many valence electrons. I'm not going to test you on that in this class, but in chemistry, I'm pretty sure they're going to test you on that. So this is why but what I'm getting at is that atoms like to have a certain amount of, they tend to prefer certain numbers of electrons depending on which type of atomic element it is. Especially ions, they tend to have their favorite number of electrons. Fluorine likes to actually take on an additional electron. So here we have fluorine and we add 10 electrons. So remember, protons are positive, electrons are negative. What's plus positive 9 minus 10? So 9 minus 10, what does that result in? So again, this is what we have. Oh yeah, let's rewind a bit. An ion is basically an atom in which the number of protons is different from the number of electrons. So again, we have 9 protons, we have 10 electrons, those numbers are different. So what's the overall charge of this ion? So again, 9 minus 10 is negative 1. So when you have a fluorine ion, it is typically negative 1 charge. Why? Because you have negative 10 plus 9, that's the overall charge of negative 1. So that's why when you see something, a number plus, so it will have not only a number, if it doesn't have a positive or negative sign, typically it just means, it should have actually, it would be irresponsible to not have a positive sign, but it is important whether an ion charge is positive or negative. All right, so here we have sodium. So again, 11, so how many protons do you think it has? Atomic number 11, therefore it has, therefore it has 11 protons. Now think about, here we have 11 electrons and count them 11. But the thing about sodium, it tends to lose 1. So instead of having 11 electrons, now it has 10. We have 11 protons, we have 10 electrons. We have an unequal amount of protons and electrons. So therefore, we now have a sodium ion. What is the overall electrical charge? So again, protons are positive, electrons are negative. What's 11 minus 10? So that is positive 1. So again, not negative 1. So the sign does matter. So yeah, in the upper right corner right here, if you just see the positive by itself with no number, that means it's probably positive 1. Or just like fluorine, we didn't have a number, it's negative 1. But if you have something like calcium, calcium tends to lose 2 electrons, so it tends to be plus 2 ionic charge compared to calcium if it had an equal amount of protons and electrons. So ions, again, by definition, have different amounts of protons and electrons. Now here we have hydrogen. So what we have with hydrogen, a sample hydrogen atom, In this starting state, we have one proton, one electron, right? So 1 minus 1, 0. No overall charge in this hydrogen atom. But things that hydrogen can be converted to a hydrogen ion, and this happens all the time in the body. So what happens with the hydrogen? Well, it tends to lose that electron. So if hydrogen loses an electron and is now just left with its nucleus, what's this overall charge? Is it an ion? Yeah, it's definitely an ion because, again, 1 is not equal to 0. But 1 minus 0 is plus 1. So here we have a hydrogen ion with a positive 1 charge. So the other twist is that, look at this, 99.9% of all the hydrogen atoms in the universe actually has no neutron. So it's not a nucleus, it's a nucleus, but just a proton. So this is why you might often, and I do this interchangeably too, hydrogen ion equals H plus equals protons, because again, if this hydrogen does not have a neutron to begin with and it loses its electron, it just becomes a naked proton with nothing else. So this is why hydrogen ions are typically protons in the human body. All right, so let's talk about molecules and compounds. So chemical bonds. So the way I like to think of it, when you form a bond with someone, it's some sort of relationship. It doesn't necessarily need to be a romantic bond, but some sort of bond, some sort of relationship. So I like to think of it this way. Chemical bonds are relationships between atoms. So these are attraction between atoms. Is there a test on Monday? No, we don't have a test on Monday. So then we have two or more bonded atoms right here. So a molecule is when you have a relationship between two atoms and they're bonded together. So as long as there are more than two atoms stuck together with a bond, it's a molecule. And an element, so this is when you have a compound, or not chemical compound, you have a chemical with only one type of atomic element. It could be a single atom, it could be multiple atoms, but as long as there's only one type of atom in that chemical, it's called an element. And then you also have compounds. So compounds are when you have more than one type of element. So you can't have something that's both an element and a molecule. You can't have something that's both a compound and a molecule. But element and compounds, these are mutually exclusive. Element has to be purely one type of atom, whereas a compound, multiple types of atoms, two or more. All right, so is this an element, molecule, or compound? Well, look at it. Does it have multiple types of atoms? No, it only has two hydrogen, right? So therefore it is an element, not a compound. But is it a molecule? Yeah, there are more than one atom right here, so it is a molecule. So something can be both an element and a molecule. Now here we have H2O, water. So is this an element? Well, again, we have two different types of atoms, so it's not an element, it's a compound. But is it a molecule? Yep, it is a molecule because, again, you have multiple atoms linked together. Now here we have monatomic oxygen. This is rare in nature, but here we have a single oxygen molecule or oxygen atom. So is it element, molecule, or compound? Is it element? Yeah, it's an element because it's by itself. But is it a molecule? No, it's not a molecule because, again, there's only one atom. But the oxygen we breathe, this is typically O2 gas. So there are two oxygen atoms linked together. Is it an element? Yes, it's still an element, but is it a molecule or a compound? Well, it's a molecule, but it's not a compound because why? Again, we have only one type of atom here. It's an element. Now here we have ozone. Is this a element? Yeah, it's still an element, even though even though it looks weird, it's still an element because it only has oxygen. Is it a molecule? Yep, it's still a molecule because it has multiple bonds, and even though there are more than two or more bonds here, it's not a compound because, again, it only has oxygen atoms. So molecules and compounds, so again, we cover chemical bonds, molecules, elements, and compounds. Ooh, it's almost 2:20, so let's do this really, really quick. So if you're not logged on Top Hat, don't worry about this. But let's see. All right, so I'm going to remember top hat join code over here. Okay, is this an element, compound, or molecule? All right, so again, don't worry if you missed it. So most of you said it's an element, some of you said it's a molecule, and again, it is an element. Why? Because one, there's only one atom in this, and two, it's only a helium atom. Right, next one. So how about this? Is this an element, compound, or molecule? And multiple answers, so select all that apply. It might be all three, it might be one, it might be two, it might be zero. So, okay. So again, don't worry about if you didn't get it in time. So some of you said it's element, most of you said it's a compound, and some of you not as much said it's a molecule. And it is both a compound and a molecule. Again, it's not an element because you have a mixture of sodium and chloride. It is a molecule because you have multiple atoms here in sodium chloride. Okay, next question. So this is H2CO3, carbonic acid. Okay, let's see how everyone did. So most of you said it was a compound, and some of you, a little fewer, said it's molecules. Some of you said it's an element. And it's both a compound and molecule. Again, element has only one type of atom, right? So then there you see both carbon, you see oxygen, you see hydrogen. It is a compound. It's also a molecule because you have many bonds linking. You have more than one atom there, so therefore it's a molecule. All right, last chance. So here we have two oxygen atoms, but this oxygen is negatively charged. So this is actually what we call superoxide. Is this an element, compound, or molecule? All right, so it seems like most of you said it's an element and a molecule, and you're correct. So it is an element because you only have oxygen atoms, you don't have anything else there, and it's still a molecule because you have more than one atom. So even though that negative charge is there, that's just another electron added to the whole chemical compound or chemical molecule. So again, this is why these are definitions. If it's more than one, it's an element if there's only one type of atom. It's a compound if there's multiple types. Molecules, there's again multiple atoms linked together. As long as there's two or more atoms linked together, it's a molecule.